Welcome to the extraordinary and awe-inspiring world of modern skyscraper construction. Here, in the hearts of major cities around the world, magnificent architectural marvels rise hundreds and even thousands of meters into the sky, reaching heights that would have seemed absolutely impossible just decades ago. These are not simple buildings constructed with basic methods. They are incredibly complex engineering achievements that combine remarkable structural innovation, advanced materials science, sophisticated mechanical and electrical systems, and the coordinated effort of thousands and thousands of skilled workers, engineers, and specialized technicians. Today, we will take you on a comprehensive and detailed journey through the complete process of constructing a modern skyscraper, from the very initial moments of careful site analysis and preparation, through foundation excavation that might extend tens of meters below street level, continuing through the meticulous assembly of the steel or concrete structural frame that rises story after story toward the sky, proceeding through the installation of thousands of mechanical and electrical systems that make the building function, and culminating in the finishing of interior spaces and the grand opening of the completed building. Watch as massive cranes, some standing as tall as the buildings themselves, reaching hundreds of meters into the sky, lift enormous steel beams and heavy materials weighing hundreds of tons to heights of hundreds of meters above the ground. Observe the coordinated ballet of construction workers, skilled engineers, equipment operators, and safety personnel working in perfect synchronization and cooperation to build ever upward, defying gravity and the laws of nature. Witness the installation of extraordinarily complex mechanical systems. The elevator systems that allow people to travel hundreds of meters vertically, HVAC systems that maintain comfortable temperature and humidity throughout the building, extensive electrical networks that power everything, and intricate plumbing infrastructure that provides water and removes waste. This is modern skyscraper construction at the absolute highest level of architectural and engineering achievement. This is the story of human ambition, architectural vision, engineering innovation, and unwavering determination to create structures that literally define city skylines and provide homes, workplaces, and services for hundreds of thousands of people. This is construction on a scale and with a precision that represents the pinnacle of modern building technology and represents humanity's command over materials and forces. Before a single shovel ever touches the earth, before any equipment is moved into position at the site, before any worker sets foot on the construction area, extensive and comprehensive analysis and planning must occur. The site for a skyscraper is analyzed with meticulous care using cutting-edge geological and geotechnical investigation methods that have been refined over decades. Geotechnical engineers arrive at the site with specialized equipment to investigate the soil and rock conditions existing beneath the surface. These engineers understand that the foundation must be strong and stable, and they must know exactly what conditions exist underground. Boreholes are drilled at multiple strategic locations across the site using specialized drilling equipment. These boreholes extend to depths of many meters, sometimes 10, 20, or even 50 meters or more, depending on the building's weight and the soil conditions. As drilling progresses, soil and rock samples are carefully extracted and immediately labeled with precise depth information. Watch as drilling equipment creates boreholes at multiple locations across the site. The drill rig, a substantial piece of equipment with a tall mast, is positioned carefully on the site. The drill bit, rotating at high speed, descends slowly but persistently into the earth, penetrating through different soil layers. As the drilling progresses deeper, the resistance increases as different layers are encountered. The drill operator monitors the drilling carefully, noting changes in resistance and drilling speed. Samples are extracted at regular depth intervals, every meter or every few meters depending on the investigation plan. Each sample is immediately bagged and labeled with the depth at which it was extracted, the date, and the borehole location. These samples provide invaluable information about the soil composition at various depths. As the collection of samples grows, a picture of the subsurface conditions emerges. Topsoil sits at the surface, loose material unsuitable for bearing building loads. Below that might be clay, a compressible material that must be excavated to reach firmer ground. Deeper might be sand or gravel providing better bearing capacity. Eventually, at significant depth, bedrock might be encountered, solid rock that will provide excellent foundation support. The extracted samples are carefully transported to a geotechnical laboratory where they are analyzed in great detail. In the laboratory, soil engineers perform a battery of tests to determine the soil properties. The bearing capacity test measures how much weight the soil can safely support without excessive settlement. The soil composition is analyzed to determine what types of particles are present. The moisture content is measured. The density of the soil is determined. The results of these tests inform the structural engineer about what type of foundation system is appropriate. Seismic testing is performed in areas where earthquakes are a concern. Specialized equipment creates controlled vibrations, either through small explosions set off at specific locations, or through specialized vibration equipment that shakes the ground deliberately. Sensors positioned around the site measure how the vibrations travel through the ground and how the vibrations are modified by different soil and rock layers. The results inform engineers about the structural characteristics of the soil and rock and help determine seismic design requirements for the building, how rigid the building must be, what type of seismic damping might be needed, and whether special foundation systems might be required. Environmental investigations are conducted to identify any contamination or hazardous materials that might exist in the soil or groundwater. The site must be safe for workers and the surrounding community. Soil samples are tested for contaminants. Groundwater samples are analyzed. If contamination is found, remediation specialists develop a plan to clean the site. Contamination might be removed by excavation and disposal. Alternatively, contamination might be treated in place using specialized techniques. The environmental investigation and any necessary remediation must be completed before construction can safely proceed. Utility surveys are performed methodically to locate existing underground utilities, water pipes distributing potable water from the municipal system, sewer lines carrying wastewater away, electrical conduits carrying power, natural gas lines, and telecommunications cables. These utilities must not be disrupted or damaged during construction. Utility companies are contacted and asked to mark the locations of their facilities. Surveyors and engineers then mark these utilities on the ground using paint or flags so construction workers can see them. During construction, extreme care is taken to avoid damaging these critical utilities. Site preparation begins with clearing vegetation. Trees and shrubs must be removed. Any grass is graded away. The site is cleared of vegetation down to bare earth. If existing structures occupy the site, they must be demolished. Demolition contractors carefully dismantle existing buildings or structures, salvaging materials where possible, removing copper wire and pipes that have recycling value, removing usable wood, and disposing of waste responsibly at appropriate facilities. The site must be completely clear before excavation begins. Erosion control measures are installed before any major ground disturbance occurs. Temporary fencing surrounds the construction site, keeping unauthorized people out and containing construction dust within the site boundary. Sediment control barriers, specialized fabric barriers designed to filter soil-laden water, prevent soil from washing away in rain events. Dust control measures, sometimes including misting systems that spray water to suppress dust. minimize dust generation during dry conditions. These environmental controls protect nearby properties and the surrounding community from construction impacts. Temporary facilities are constructed at the site to support the construction effort. A construction trailer serves as the site office where project managers, engineers, and administrative staff work. Inside the trailer, plans are reviewed, schedules are managed, and daily construction decisions are made. Storage areas are prepared for equipment and materials that will be needed during construction. Temporary access roads are constructed to allow construction vehicles to enter and exit the site efficiently. Parking areas for worker vehicles are designated, sometimes requiring temporary parking facilities. A temporary electrical system is installed to power construction equipment and temporary lighting. A comprehensive safety plan is developed and implemented before construction begins. Safety is absolutely paramount. Construction is inherently dangerous work and every precaution must be taken to protect workers. All hazards are identified and assessed. Training is provided to all workers about the specific hazards they will encounter and the safety procedures they must follow. Personal protective equipment is required. Hard hats to protect from falling objects, safety vests in bright colors for visibility, safety glasses to protect eyes, gloves to protect hands, and steel-toed boots to protect feet. For work at heights, harnesses and lanyards are required. For certain specialized work, respirators or other protective equipment might be needed. Safety inspections are conducted regularly by safety officers to ensure safety procedures are being followed and hazards are being controlled. The site is surveyed and staked out with extreme precision. Professional surveyors using GPS technology and precision laser equipment establish the exact location of the building on the site. The building's corners are marked. The center line of the building is marked. Temporary benchmark markers are placed at strategic locations to establish reference points for all future measurements. Every element of the building must be positioned accurately relative to these benchmarks. The precision of this initial surveying work affects the entire construction. If the building is positioned incorrectly, structural components won't align properly during assembly. The foundation is absolutely the most critical part of the entire building. The foundation must support the tremendous weight of the entire structure, potentially thousands of tons or more for a tall building. If the foundation fails, the entire building will fail catastrophically. Foundation work begins with excavation, the systematic removal of earth to the depth required by the structural engineer's calculations. For tall buildings, the foundation might need to extend tens of meters below the street level, perhaps 30, 40, or even 50 meters deep depending on soil bearing capacity and building weight. This requires excavating an enormous pit. Massive excavation equipment arrives at the site, large front-end loaders with buckets several meters wide, enormous excavators with long booms and large buckets, and heavy-duty dump trucks capable of carrying 30 to 40 tons of excavated material. The excavation work must be done carefully and methodically. Excavating too shallowly risks settlement and building damage as the building weight compresses the soil. Excavating deeper than necessary wastes enormous amounts of time and money, and deeper excavation increases the cost significantly. Watch as excavators remove soil carefully and methodically day after day. The bucket of the excavator digs into the earth with tremendous force, penetrating into the soil. The bucket fills with soil and rock, becoming progressively heavier. The hydraulic arms of the excavator lift the heavy bucket and rotate the machine body. The bucket is positioned over a dump truck waiting below. The bucket opens hydraulically and material tumbles down into the truck bed with a thunderous sound. The truck settles lower under the weight of the load. Once the truck is filled to capacity, the operator drives away, heading to the disposal site miles away. Another empty truck immediately arrives at the excavation to receive the next bucket of material. The excavation continues methodically, hour after hour, day after day, week after week. The excavation creates a massive pit that grows progressively larger and deeper. The walls of the excavation pit must be stable and strong. If the walls collapse, they can bury equipment and workers, causing catastrophic accidents and potentially killing people. For deep excavations, the walls are supported by steel sheet pilings, long sheets of steel driven into the ground to create a continuous retaining wall that supports the earth behind them. Alternatively, soldier piles, vertical steel beams spaced at intervals, are driven into the ground with wooden or steel lagging boards or sheets, installed between them to form a retaining wall. Some deep excavations use slurry walls, concrete walls created in place using specialized excavation and concrete techniques. The slurry wall is created by digging a trench while a thick slurry keeps the trench walls from collapsing. Then reinforcing steel is placed in the trench and concrete is poured, displacing the slurry. Dewatering is often necessary because groundwater accumulates in the excavation pit as the pit extends below the water table. Water seeping into the pit makes work difficult, unsafe, and impossible. Large dewatering pumps are positioned around the pit. The pumps remove water continuously and relentlessly, discharging it to storm drains or nearby surface water. As water is pumped out, the water table in the excavation area is lowered. The dewatering must be controlled carefully and conservatively because removing too much water from surrounding soil can cause settlement of nearby buildings. Buildings adjacent to the construction site must be monitored to ensure they are not being damaged by dewatering. As excavation reaches the required depth, which might take months for very deep excavations, the excavation floor is prepared carefully. The soil is leveled and smooth. Settlement monitoring points are established. The bearing capacity of the exposed soil is verified by testing to ensure it matches predictions from the initial borehole investigation. If the soil encountered is weaker than expected, deeper excavation might be necessary. If the soil is stronger than expected, the excavation depth might be acceptable as planned. The subgrade, the prepared earth surface at the bottom of the excavation, must be capable of safely supporting the foundation and the building weight above it without excessive or uneven settlement. A geotechnical engineer conducts a final comprehensive inspection of the completed excavation. The engineer examines the soil and rock exposed in the excavation walls, noting color, composition, and characteristics. The engineer verifies that the actual conditions match the predictions from the borehole samples. The bearing capacity is confirmed through testing. Approval from the geotechnical engineer, documented in writing, is a critical prerequisite before the next phase can begin. Without this approval, construction cannot proceed. Pile foundations are sometimes required for very tall buildings, or when soil bearing capacity is insufficient, or when the building will experience heavy concentrated loads. Piles are long structural elements, either steel or concrete, that are driven or drilled into the ground to reach deeper, stronger soil or rock layers capable of supporting tremendous loads. Pile driving equipment uses large heavy hammers to repeatedly strike the tops of steel piles, driving them progressively deeper into the ground. Alternatively, drilling equipment creates large diameter holes that are then filled with reinforcing steel and concrete, creating drilled piers or caissons. Watch as pile driving equipment positions a steel pile, a long section of steel pipe or H-beam, perhaps 15 or 20 meters long, painted bright colors for visibility. The pile is a long structural element weighing many tons. The hammer, suspended high above the pile on the pile driving rig, is positioned above the top of the pile. The hammer, weighing hundreds of tons itself, is lifted by powerful hydraulic equipment. When released, the hammer falls freely under gravity, accelerating rapidly. When the hammer strikes the top of the pile with tremendous force, the impact sends the pile downward into the ground. The impact sound is deafening, a tremendous crash that echoes across the site. The pile descends slightly into the ground. Immediately, the hammer is lifted again. The cycle repeats: lift, drop, impact, descend. Blow after blow, the pile is driven deeper and deeper into the ground. The process continues for hours until the pile reaches refusal, the point where it can no longer be driven deeper because it has reached hard rock or very dense soil that cannot be compressed further. The completed piles are verified by testing to ensure they can support the design loads. Dynamic testing measures how the pile responds to the hammer blows and how far the pile settles with each blow. As the pile reaches refusal, each blow moves the pile only millimeters and the blow count increases. Static load testing applies enormous slow loads to the pile and measures how much the pile settles under that load. The testing confirms the pile can support the design load safely and that excessive settlement will not occur. Pile caps are constructed on top of the piles, creating the critical connection between the piles deep underground and the building structure that will rest above them. These reinforced concrete structures distribute the building's weight to the piles. The pile cap must be large enough and strong enough to distribute concentrated building loads to multiple piles. The pile cap is designed and constructed by reinforced concrete specialists. The structural frame, the skeleton of the building, is erected next. For many modern skyscrapers, this is a steel frame made of steel columns and steel beams. The steel frame provides the structural strength that allows the building to rise hundreds of meters into the sky and support the weight of all components, occupants, and forces acting on the building. Steel components arrive at the site in fabrication trucks. The structural steel has been fabricated off-site in a specialized steel fabrication shop where each beam and column has been cut to exact length, holes have been drilled precisely for bolted connections, and other fabrication work has been completed. The components are organized and stored on site in organized areas, with each piece labeled clearly so workers can identify exactly what component is needed. The first structural members are positioned on the prepared foundation with extreme care. Steel columns, large vertical beams that might be as large as a human is tall and very heavy, are positioned vertically. The columns must be perfectly vertical. A slight deviation from vertical will accumulate as the building rises story after story, potentially causing serious problems in alignment and structural performance. Watch as a large steel column is lifted by a massive tower crane. The column, perhaps as long as a truck trailer and weighing hundreds of tons, is suspended from the crane hook by multiple steel cables arranged in a special lifting configuration. The crane operator, speaking constantly with spotters via radio, carefully positions the column. Workers on the ground guide the column's descent using tag lines. Ropes attached to the column to stabilize it and prevent swinging. The column descends slowly, very slowly, the crane operator making minute adjustments. Workers on the ground direct the column toward its position. The column rests on the foundation or on a base plate bolted to the foundation. Workers insert temporary bracing to hold the column in position and ensure it remains perfectly vertical. Once the first column is in position, additional columns are positioned around the floor level. The columns might be arranged in a grid pattern, positioned at regular intervals across the floor. Each column must be positioned with millimeter precision so that the building's geometry is perfect. The columns are bolted together at their connection points using large bolts and steel connection plates. The bolts are tightened with hydraulic torque wrenches to ensure proper connection strength. Multiple bolts are used to distribute the load. Steel beams are then positioned between the columns. These horizontal beams will support the floor structure and transfer floor loads to the columns. The beams span from column to column, creating the framework for each floor. Each beam must be positioned at exactly the right height to maintain proper floor-to-floor heights throughout the building. Deviation in height would create sloping floors or inconsistent ceiling heights. Watch as a massive steel beam is lifted by the crane. The beam might be 20, 30, or even 40 meters long and can weigh hundreds of tons. The crane operator must have extraordinary skill to handle such a large, long, heavy load. As the beam is lifted, it swings slightly. The crane operator and spotters must control the swing carefully. Workers guide the beam's descent. The beam slowly descends into position between two columns. Connection bolts align the beam with connection plates welded to the columns. Workers slide bolts through the aligned holes. Nuts are threaded onto the bolts. Hydraulic wrenches tighten the bolts to proper specification. The connection must be strong enough to safely carry all loads. As beams are positioned, additional diagonal bracing is installed. This bracing provides lateral support, preventing the structure from swaying excessively in wind or during earthquakes. The bracing is carefully calculated by engineers to provide the necessary stiffness and strength while maintaining clear space in the building. Without adequate bracing, the building would be flexible and sway excessively, making occupants uncomfortable and potentially causing structural problems. The completed structural frame for a floor level is a strong, rigid grid of columns and beams, creating a framework capable of supporting tremendous loads. This frame is repeated story after story, rising higher and higher. The frame grows steadily as additional stories are added. After several stories have structural frames in place and some temporary decking is installed, construction can proceed on lower floors, installing floors, walls, and mechanical systems, while the frame continues to rise above. This allows the project to proceed efficiently with multiple work fronts active simultaneously. Safety is absolutely paramount during frame erection. Workers at height must wear fall protection equipment, harnesses connected by lanyards to anchor points so they cannot fall. Temporary platforms and walkways provide safe working surfaces. Safety nets might be installed below work areas to catch any falling objects or workers. Strict protocols govern who is permitted on the steel during erection and what personal protective equipment they must wear. Safety briefings are held daily. Near-miss incidents are reported and investigated so lessons can be learned. Quality control inspections verify that all connections are properly made. Professional inspectors check that bolts are tightened to proper specifications, using calibrated torque wrenches to verify correct tension. Inspectors verify that the structure remains plumb, perfectly vertical, and true without deviation or twist. Any deficiencies found are corrected immediately. The structural frame must be perfect because any errors or deficiencies would propagate through all subsequent construction. Once the structural frame for a floor is in place, the floor structure is installed. For steel frame buildings, this typically involves pouring concrete on a steel deck. The steel deck is a thin steel sheet that spans between the steel beams, providing formwork, a form or mold for the concrete that will be poured on top. The steel deck is carefully positioned on top of the steel beams, spanning between them. The deck is fastened to the beams using fasteners or welds so it cannot move. Temporary shoring, temporary vertical supports the deck from below until the concrete hardens and becomes self-supporting. The weight of the concrete and workers is tremendous, and the shoring must be adequate to support all loads. The deck is carefully inspected to ensure it is properly positioned and fully supported. The deck must be clean and free of mud or other contaminants so the concrete will bond properly. Temporary rebar, steel reinforcing bars, is positioned on top of the deck in calculated patterns. These rebar provide additional strength to the concrete slab. In locations where loads are concentrated, additional rebar is placed. Watch as concrete is delivered to the floor level continuously. Concrete trucks arrive at the base of the building. The concrete, a mixture of cement, sand, gravel, and water that is plastic and workable but will harden into rock-like strength, is transferred to a pumping truck, a specialized truck with a long boom and powerful pump that can deliver concrete to high elevations. The boom extends toward the building and upward. The pump forces concrete through a long hose that carries it to the floor level being worked on. Workers on the floor direct the discharge of concrete. The concrete flows onto the floor, spreading across the steel deck and reinforcing steel. Workers spread the concrete across the entire floor using rakes, shovels, and other tools. The concrete must fill all spaces and be properly consolidated so no voids remain. Concrete vibrators, handheld devices that vibrate at high frequency, are used to consolidate the concrete and remove air bubbles. Without proper consolidation, air bubbles would remain in the concrete, creating weak spots. The vibration process is performed methodically across the floor. The concrete is vibrated until no more air bubbles rise to the surface, indicating proper consolidation. The concrete surface is screed level using a long straight edge. A worker, or sometimes mechanical equipment, drags the straight edge across the fresh concrete, removing excess concrete and leaving a level surface. The finished surface must be level within specified tolerances. Once screeding is complete, the concrete is allowed to cure, hardening into a strong, durable floor structure. The curing process takes time, typically several days for concrete to develop sufficient strength. During the curing period, the concrete is monitored and protected. If weather is extremely hot, the concrete might need to be kept moist to prevent rapid drying, which could cause cracking. If weather is cold, heating might be needed to maintain proper curing conditions. While the concrete is curing and hardening, workers on lower floors begin installing permanent structure and systems. The productivity is remarkable. As one floor awaits concrete curing, work proceeds on lower floors. Different trades work simultaneously: carpenters installing framing, electricians installing wiring, plumbers installing plumbing lines. The coordination required is complex but necessary for project efficiency. The exterior enclosure is installed to protect the interior from weather. Exterior walls are built, either from masonry units like brick or concrete block, or from curtain wall systems of glass and aluminum. The exterior wall is installed floor by floor as the building rises. Exterior walls must be weather-tight, preventing rain and water infiltration while allowing the building to move slightly in wind and earthquakes. 4 curtain wall systems. Modern exterior walls that are very common on tall buildings. Aluminum mullions are installed, creating a framework on the face of the building. These mullions are vertical and horizontal aluminum members that create a grid pattern on the building facade. The mullions are attached to the structural frame behind them. Glass panels are carefully inserted into the framework created by the mullions, creating the transparent exterior surface visible from outside the building. Some panels are fixed, permanently in place. Other panels are operable windows that open for ventilation, allowing fresh air to enter occupied spaces. The curtain wall must be weather-tight, preventing water infiltration. It must be strong enough to withstand wind pressure. It must move slightly with the building's movement without tearing or breaking. Watch as workers install curtain wall on a specific floor. Workers on suspended platforms attach the aluminum framework to the building structure. The framework is positioned with extreme precision so the building appears uniform and aligned when viewed from a distance. The mullions are checked for vertical and horizontal alignment. Glass panels are carefully handled. glass is fragile and can be damaged easily. The panels are positioned in the framework and secured with fasteners or gaskets. The installation must be done with meticulous care because glass panels are valuable components and replacement is expensive. The exterior enclosure also includes doors, windows, mechanical louvers for ventilation and equipment discharge, and other architectural elements. Each of these elements must be precisely positioned and properly sealed to prevent water leakage. Water infiltration would damage the building interior and create mold problems. The sealing work is critical and must be done by experienced technicians. As the structural frame is complete and floors and walls are in place, mechanical systems must be installed. These systems make the building comfortable and functional. They include HVAC, heating, ventilation, and air conditioning systems, plumbing systems, and electrical systems. The complexity is remarkable. A large building might have thousands of components in these systems. The HVAC system is absolutely critical for comfort and air quality. Occupants spend most of their time indoors, and the air quality and temperature must be maintained within comfortable ranges. Large rooftop equipment, chillers that provide cooling, boilers that provide heating, and air handling units that process and distribute air, provide heating and cooling to the building. These units are connected by extensive piping carrying chilled water from the chiller, hot water from the boiler, and steam for heating in some locations throughout the building. Watch as rooftop mechanical equipment is installed. Large pieces of equipment, some weighing many tons, some taking up enormous floor space, are lifted by crane to the roof. The equipment is carefully positioned and bolted down securely so it cannot move. The positioning is critical. Each piece must be properly connected to supply and return lines, must be properly supported structurally, and must be accessible for maintenance. Piping runs from the rooftop equipment down through vertical chases. Vertical passages running through the building specifically designated for mechanical systems. These chases extend from the roof to the basement, carrying pipes to every floor. The piping is insulated to minimize heat loss and is supported at intervals by brackets. The piping must be protected from physical damage and must be accessible for maintenance. On each floor, smaller piping branches off from the vertical chases. The piping is routed to air handling units on that floor or in that zone. The air handling units contain filters to clean the air, cooling coils where air is cooled, heating coils where air is heated, and fans that move air. The fans push air through the coils where it is heated or cooled based on season and temperature requirements, then distribute the conditioned air throughout the floor through ductwork. The ductwork, large sheet metal ducts, carries air from the air handling unit to individual rooms and spaces. The ducts are routed through ceilings, above suspended ceilings, or within walls. The ductwork must be properly sealed so air does not leak out. The ducts must be supported and braced so they do not vibrate excessively. Terminal devices in each room control the amount of air flowing into that space, providing individual zone control. Different spaces can have different temperatures. Some spaces cool while others are heated, depending on the needs and preferences of occupants in those spaces. Plumbing systems deliver potable water throughout the building and remove wastewater. Water enters the building at the base and is pumped to rooftop storage tanks located on the roof. From the storage tanks, water flows down throughout the building due to gravity, supplying sinks, toilets, showers, and other fixtures. The water must be delivered at adequate pressure and temperature. Pressure regulators maintain constant pressure. The water must be clean and safe for human consumption. Filtering systems remove particles and sediment. Hot water is produced by large boilers or solar heating systems located on the roof or in mechanical rooms. Hot water piping runs throughout the building, supplying hot water to fixtures and to the HVAC system for heating. The piping must be insulated to minimize heat loss and maintain water temperature as it travels through the building. Insulation around hot water pipes prevents heat loss and prevents burns to people who might touch the hot pipes. Wastewater piping collects water from sinks, toilets, showers, and other fixtures, conveying it to the building sewer system that connects to the municipal sewer. The piping must slope properly to allow gravity flow. Wastewater must flow downward to drain properly. The piping must be protected from freezing in cold climates. Trap seals, water seals and pipes below fixtures prevent sewer gases from entering the building through drains. Rainwater from the roof must be managed to prevent water damage. Roof drains collect water from the roof and conduct it through vertical piping to the storm sewer system. Overflow management ensures water doesn't accumulate on the roof if the main drainage system becomes blocked. Proper management is essential to prevent leaks and water damage to the building. The installation of mechanical systems is complex and requires skilled workers. Plumbers, pipe fitters, and mechanical technicians work together in a coordinated fashion. Each system component must be positioned precisely. Each connection must be properly made and sealed to ensure no leaks. After installation is complete, the systems are pressure tested to verify no leaks exist. The testing involves pressurizing the systems and monitoring for any drop in pressure that would indicate a leak. Electrical systems are installed to provide power to the entire building. Lighting for visibility, equipment for operation, heating and cooling systems, elevators for vertical transportation, and countless other electrical needs. The electrical system for a large building is remarkably complex, involving a main service entrance where power enters from the utility, large transformers, main distribution panels, and circuits running to every space in the building. The main electrical service enters the building at a designated location, typically a ground floor or basement mechanical room. A large transformer steps down the utility voltage to the voltage used within the building. The transformer is typically mounted in a transformer vault, a room designed to contain the transformer and its cooling systems. The transformer is filled with insulating oil for cooling and insulation. Large electrical cables connect the transformer to the distribution equipment. From the main electrical service and transformer, large cable runs to the main electrical distribution panel, the central point where electrical power is distributed to various sections and zones of the building. The panel is a large cabinet containing multiple components and circuit breakers. The main electrical service panel contains main breakers that can disconnect power to the entire building if needed for maintenance or emergency. Branch breakers protect individual circuits supplying power to different areas of the building. Watch as electricians install electrical cable and cable trays and protective conduits. Large trays fabricated from aluminum or steel run along the ceilings of mechanical spaces, safely supporting the main power distribution cables. The cables are enormous, several centimeters in diameter, carrying thousands of amperes of current. Smaller conduits branch off from the main trays, carrying power and control signals to individual floors. The cable is organized and labeled, with color coding identifying the circuit purpose. Everything must be organized so maintenance technicians can understand the system years later. Lighting circuits are installed in each space throughout the building. Wiring is routed through walls and ceilings to light switches and light fixtures. The wiring must be properly supported and protected from physical damage. Junction boxes where wires are spliced must be accessible for future maintenance and changes. Electrical codes specify exact requirements for wire sizing, support spacing, and protection methods. All work must comply with these codes. Emergency power systems are absolutely critical. A diesel-powered backup generator, located in a mechanical room and capable of generating enormous power, provides backup electrical power if utility power fails. The generator automatically starts if power is lost, maintaining power to emergency lighting for safe exit, fire suppression systems for safety, and elevator systems so people can exit the building. The generator is tested regularly to ensure reliable operation when needed. Power outlets are installed in each space, electrical receptacles where equipment can be plugged in. The outlets must be positioned conveniently so cords do not present tripping hazards or interfere with equipment operation. In offices, outlets are positioned along walls. In meeting rooms, floor-mounted outlets might be installed. In data centers, raised floors contain cable management systems with abundant outlets for equipment. Lighting systems are installed and tested throughout the building. Different spaces have different lighting requirements and different aesthetic goals. Offices might have task lighting combined with general illumination so workers can see clearly. Hallways have safety lighting at a lower level that provides visibility without causing glare. Stairwells have bright lighting for safety so steps are clearly visible. Elevator lobbies have attractive lighting creating welcoming spaces. The lighting is controlled by switches, motion sensors that turn lights on when occupancy is detected, or daylight sensors that adjust lighting based on natural light levels, reducing energy consumption. Building security systems, fire detection systems, and advanced building management systems are installed and integrated. These systems are connected to a central control point where building operators monitor building status continuously. The control systems allow remote operation of building functions. Security cameras provide surveillance of public spaces and entrance areas. Access control systems manage who can enter different areas of the building. Fire detection systems monitor for smoke or heat. As structural work and major systems are complete, interior finishes are installed. The materials and details that make the building attractive, comfortable, and functional. These finishes are what occupants see and touch every day. Drywall is installed on interior walls, covering the structural framing and hiding the mechanical and electrical systems that are concealed within the walls. The drywall provides a smooth surface for painting and provides fire separation between spaces, slowing fire spread between spaces if fire occurs. Drywall is installed in large sheets, typically 1.2 meters wide and 2.4 meters tall, fastened to the framing with screws spaced at regular intervals. Multiple sheets are positioned side by side to cover wall areas. Watch as workers install drywall. Two workers carefully lift a large drywall sheet and position it against the wall frame. One worker holds the sheet firmly in position while the other operates a power screwdriver, driving screws into the framing at the specified spacing. The sheet is secured at multiple points around its perimeter and at intermediate framing members. Adjacent sheets are positioned tightly against each other. Sheets are cut carefully to fit around door and window openings using specialized drywall saws. After all drywall is installed on a wall, the joints between sheets must be finished. A drywall finisher applies joint compound, a special plaster-like material, with a wide knife, covering the joint between sheets and the screw holes. The compound is allowed to dry, then is sanded smooth to remove any imperfections. Multiple coats might be applied, with sanding between each coat, until the joints are completely seamless and invisible. This taped and mud finish is highly skilled work requiring considerable experience to achieve quality results. Poor finishing work is visible and unprofessional. Painting is performed throughout the building. A primer is first applied to provide proper adhesion and coverage. Then finished paint is applied, typically 2 coats for durability and coverage. Different colors might be used in different spaces for aesthetic and functional reasons. Brightly colored walls in children's areas versus neutral tones in offices. Quality painting requires skill to achieve uniform coverage without drips or sags. Poor painting work is immediately visible and creates a poor impression. Flooring is installed throughout the building. Different spaces require different flooring materials based on function. Carpet is installed in offices and meeting rooms for comfort and sound absorption. Tile is installed in bathrooms and kitchens because it is water-resistant and easy to clean. Polished concrete might be used in some commercial spaces for a modern aesthetic. Vinyl flooring provides durable, cost-effective flooring in utility spaces. Each flooring type must be installed properly to ensure it is level, secure, and durable. Suspended ceilings are installed in many spaces. A grid system of aluminum or steel runners is suspended from the structural deck above using wires or hangers. The runners create a regular grid pattern typically spaced 1 meter apart. Acoustic ceiling tiles are laid into the grid, creating the finished ceiling. The suspended ceiling conceals mechanical systems, electrical wiring, and structural elements while remaining accessible for maintenance. If repairs are needed to systems above the ceiling, the tiles can simply be removed for access. Interior doors and frames are installed throughout the building. Wooden or metal frames are set into the wall openings. Doors are carefully hung on hinges so they swing smoothly and latch securely. Door hardware, hinges, handles, locks, must be installed correctly. Locks must function reliably. Handles must be operable without excessive force. Each door must function properly thousands of times over the building's lifetime. Interior permanent walls and partitions are constructed as needed to create the specific layout designed for each space. These walls might be full-height structural walls that extend from floor to roof structure, or partial-height walls that provide visual and acoustic separation but allow air flow above. The walls are positioned precisely according to floor plans. Openings for doorways are framed and finished. Cabinet work and built-in furniture are installed in specialized spaces. Kitchens receive cabinetry built from wood or engineered materials and appliances for preparing food. Bathrooms receive vanities with sinks and mirrors. Specialized spaces might receive custom built-in elements designed for specific functions. The cabinet work is installed by specialists trained in precision carpentry. Permanent mechanical systems are completed and final connections are made. Ventilation terminals and air diffusers are installed in spaces where HVAC ductwork ends. These diffusers distribute air evenly into the space. Radiators or other heating elements are positioned for optimal heat distribution. The final connections of the HVAC system are completed and tested. Valves are installed and adjusted to balance the system, ensuring each zone receives the correct amount of heating or cooling. Plumbing fixtures are installed throughout the building in bathrooms and kitchens. Sinks, toilets, showers, and bathtubs are positioned according to design plans. Faucets and fixtures are connected to the plumbing lines. The fixtures are tested to verify proper operation and water quality. The fixtures must function reliably. Water pressure must be adequate. Water temperature mixing valves ensure hot water is not too hot for safety. Elevators and escalators are installed, providing the vertical transportation critical to skyscraper operation. Without elevators, tall buildings would be completely impractical because climbing stairs to upper floors would be exhausting and time-consuming. Elevator shafts, vertical passages running the full height of the building, were created as the building was constructed, with structural framing and concrete floors at each level forming the shaft. Now the elevator equipment is installed. The shaft has guide rails along the walls to guide the elevator car smoothly. The car, the chamber that carries people and freight, is suspended from cables attached to a pulley system at the top of the shaft. Watch as elevator equipment is installed in the machine room at the roof level. The counterweight, a heavy mass that balances the weight of the car, is suspended by cables over pulleys. The traction machine, the motor and pulley system, drives the cables over the pulley, raising and lowering the car and counterweight together. When the car descends, the counterweight ascends. The control system automatically positions the car at each floor when called by occupants. The elevator doors, located at each floor landing and on the car itself, are installed and tested. The doors must operate reliably and safely, protecting people from injury. Door sensors detect obstructions and prevent the doors from closing on persons or objects. Safety features prevent the car from moving if the doors are not closed. Backup systems ensure the doors can be manually opened if power fails. Multiple elevators are typically installed in a building. This provides redundancy. If one elevator is out of service for maintenance, others continue operation. The number of elevators is determined by the building's occupancy and expected traffic patterns. Building code requires a minimum number based on occupancy. More elevators are often installed to provide faster service and reduce wait times. Emergency systems are integrated with the elevators. During emergency evacuations, elevators automatically return to the lobby floor and open, allowing occupants to exit safely. In high-rise buildings, stairs must be used for evacuation. Elevators cannot be relied upon for emergency exit. Backup power ensures elevators continue operating if main power fails. Stairs are constructed and finished throughout the building. While elevators handle the routine vertical transportation, stairs provide the essential means for emergency evacuation. The stairs must meet building codes for width, step height, and handrailing. Each step must be exactly the right height so people don't stumble. The stairs must be well lit and clearly marked. Emergency lighting ensures stairs are visible even if power fails. Roof equipment is installed. Mechanical equipment discussed previously sits on the roof. Additional roof-mounted equipment might include rooftop gardens providing insulation and stormwater management, solar panels generating electricity, or mechanical systems for specialized functions. The roof membrane, the waterproof layer protecting the building from rain, is installed carefully and tested for leaks. Fire suppression systems are installed throughout the building providing life safety protection. Sprinkler heads are positioned on ceilings in all spaces, designed to open automatically and spray water if fire heats the space. The sprinkler system is connected to the water supply and to fire alarm systems. Wet standpipes, vertical pipes with connections for fire hoses, are installed in stairwells and mechanical spaces providing additional firefighting capability. Portable fire extinguishers are positioned in convenient, highly visible locations for immediate emergency use. Fire alarms and smoke detection systems are installed in every space. Smoke detectors continuously monitor air quality for smoke. If smoke is detected, the fire alarm system is activated immediately, alerting occupants and notifying emergency responders. Heat detectors in certain spaces detect high temperatures. Manual alarm stations allow people to activate alarms if needed. The system is tested regularly to ensure operation when needed. Building management systems are programmed and tested. These sophisticated computerized systems control building operations, lighting, HVAC, security, and other systems. The systems can be adjusted based on occupancy and season, optimizing energy efficiency. Occupancy sensors can reduce lighting and HVAC in unoccupied spaces. Scheduling systems can adjust temperatures during off hours when the building is unoccupied. Before occupants move into the building, comprehensive testing is performed to verify that all systems function properly and safely. Commissioning is the process of verifying that all systems work as designed. The structural system is tested for integrity. Non-destructive testing techniques verify the structure is sound. Visual inspections verify that connections are tight and no damage exists. Load testing might be performed on floors, applying test loads and measuring deflection to verify the structure performs as designed. HVAC systems are tested for proper operation. Airflow is measured using specialized instruments. Temperatures are monitored throughout the building. The system is adjusted to achieve proper temperature and humidity control in every space. Balancing is performed, adjusting dampers and valves to ensure the correct amount of air and heat flows to each space. Plumbing systems are tested for proper operation. Water pressure is verified throughout the system. Water quality is tested to ensure it meets standards. All fixtures are tested to verify proper operation and drainage. Wastewater systems are tested for proper drainage. Hot water systems are verified to deliver hot water at the proper temperature. Electrical systems are tested for proper operation. Load calculations verify that the electrical service is adequate. All circuits are tested for proper voltage and operation. Emergency power systems are tested to verify automatic operation if main power is lost. The generator is tested under full load to ensure it can provide full power. Elevator systems are extensively tested and verified. The elevators are operated through all motions: raising, lowering, stopping, door operation, emergency stops, and verified to operate safely. The safety systems are tested to verify they protect occupants. Door safety devices are tested. Emergency communication systems are tested. Backup power systems are verified. Life safety systems are tested for proper operation. Fire alarms are activated and verified to alert occupants. Emergency lighting is verified to illuminate in darkness. Evacuation procedures are tested with building occupants participating in practice drills. Escape routes are verified to be clear. Emergency supplies and equipment are verified to be in place. A building inspection and occupancy permit is obtained from municipal authorities. Municipal inspectors systematically verify that the building complies with all applicable building codes and regulations. Inspectors check structural adequacy, electrical safety, plumbing design, fire safety systems, and countless other requirements. Only after the building inspector approves and issues an occupancy permit can occupants legally move in. The building owner and occupants take possession of the completed building. Moving equipment is positioned. The first occupants begin moving into their spaces. Office furniture is delivered and arranged. The building comes alive as people occupy the spaces that were constructed for them. The completed building opens to its occupants and begins its operational life. The building will serve its purpose for decades, providing workplaces, residences, and services to thousands of people. The investment in construction is repaid through the services the building provides. The building systems begin operating under normal conditions. HVAC systems maintain comfortable temperature and humidity throughout the building. Elevators transport people efficiently between floors. Electrical systems power lighting and equipment. Plumbing systems deliver water and remove wastewater. The building operates smoothly as a complex integrated system. Building operations and maintenance begin. A building operations team is hired and trained. Building engineers monitor systems and perform maintenance. Elevator maintenance technicians service elevators regularly. HVAC technicians service heating and cooling equipment. Plumbers perform plumbing maintenance and repairs. Electrical technicians monitor and maintain electrical systems. The building requires constant attention and maintenance to remain in good condition. The building is cleaned and maintained constantly. Housekeeping staff clean floors, walls, and surfaces. The building is maintained in good condition to provide a pleasant, safe environment for occupants. Maintenance work prevents small problems from becoming large, expensive repairs. Over decades of operation, the building will be maintained and periodically upgraded. Mechanical systems will be replaced when they reach the end of their service life. Interior finishes will be refreshed and updated. Technology systems will be upgraded to current standards. The building will adapt to changing needs and occupancy requirements. A modern skyscraper represents one of humanity's greatest achievements in engineering and construction. The building stands as a testament to human ambition, creativity, determination, and capability to build structures of remarkable size and complexity. The skyscraper rises hundreds of meters into the sky, visible from miles away, dominating the urban landscape. The design of a skyscraper requires expertise in structural engineering to ensure the building is strong and safe. Civil engineering knowledge ensures foundations are adequate. Mechanical engineering expertise creates comfortable, healthy HVAC systems. Electrical engineering provides safe, reliable power distribution. Architectural expertise creates beautiful, functional spaces. The coordination of all these specialized fields is remarkable. The construction requires the coordinated effort of thousands and thousands of skilled workers. Structural steel workers who assemble the frame, concrete workers who pour floors, electricians who install power systems, plumbers who install water systems, HVAC technicians who install heating and cooling, painters and finishers who create the final surfaces, and many other trades. Each worker is essential. Each contributes their skill and effort to the project. The building will stand for many decades, perhaps a century or more. The occupants of the building will conduct business, live their lives, raise their families, and pursue their dreams within the building. The building might provide workplaces for thousands of people. It might house hundreds of residences. It might contain restaurants, retail, entertainment venues, and other uses serving the community. The building provides tremendous value. The construction of a skyscraper is never simple or easy. Countless challenges arise, whether delays, unforeseen site conditions, equipment failures, coordination challenges, budget pressures, and schedule pressures. Yet through determination and skillful problem solving, the building is completed on schedule and within budget, providing value to the community and investors. The skyline of a city is defined by its skyscrapers. These tall buildings are visible from distant locations, attracting residents and visitors, defining the city's image and character. The skyscraper is an architectural icon of the modern city. Thank you for joining us on this comprehensive journey through skyscraper construction. We hope you have gained deep appreciation for the remarkable engineering, meticulous planning, skilled coordination, and dedicated effort required to bring these magnificent structures into being.
gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Exit shift like clouds in the dark. A symphony of cogs finding their spark. Atmosphere fades like a fading dream. The hum recedes into the machine. Warmth dissolves into the still serene. A gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Tessers shift like clouds in the dark. A symphony of cogs finding their spark.